So this is another video where we're going to compute the determinant of a matrix. There's a few slight differences though. The first thing is we'll actually be working with a 4x4 matrix. So we haven't done any 4x4 determinant computations so far. So when working with larger matrices, the number of computations goes up. So it'll be kind of nice to work through an example with a larger matrix to see how to kind of organize the work in a logical way. The other thing that we're going to be doing is based on the determinant that we compute, we're going to be able to conclude if the matrix is invertible or not. So far we've focused very much on just the mechanics of the determinant computation. Now we're also going to briefly discuss what the value of the determinant tells us about whether the matrix is invertible or not invertible. So the matrix we're going to work with is the matrix A, which is a 4x4 matrix. Its first row is 1, 0, 2, 0. Second row is -4, -3, 1, 5. Third row is this, and the fourth row is this. So this is the matrix A. And like I said, we're going to compute the determinant of this matrix, and we're going to use that information to determine if A is invertible or not. So our general approach for computing a determinant is to do cofactor expansion. So I'm going to go ahead and do cofactor expansion about the first row. So we're going to do cofactor expansion. And we're going to do it about the first row. You're free to choose any row or column that you'd like. In this particular example, I really like the first row because there's a few zeros there. So I know a couple of the multiplies will end up being 0, and that will save me some computations. So in general, try to pick a row or a column that has a lot of zeros to make a lot of the cofactor expansion terms go away and save yourself some of the computations that you need to do. So let's go ahead and do the cofactor expansion. I'm going to have 1 times the determinant of this 3x3 matrix. And I'm going to have -0 times the determinant of something. But I don't really care what that something is, because 0 times anything is going to give me a 0, so I'm not even going to bother writing out what the submatrix is. Then +2 times the determinant. So we're going to cross out this and cross out this. So what's left is 4 -3, 5, -6, 2, 1, 0, 1, 0. So that's what we end up with right here. And then finally, -0 times. So normally I would put a line here, and I would put a line right here. And what I'm left with is this submatrix. But again, since it's 0 times the determinant of that matrix, 0 times anything is 0. So I'm not even going to bother writing that out. So what I really need to do here now is compute a couple 3x3 determinants. So I need to compute this term, which I'll call term 1, and I need to compute this term, which I'll call term 2. So let's go ahead and break it down into computing these individual pieces, and later we can plug into this equation right here to get the final answer that we need. So term 1, the determinant of this matrix. So again, I need to do cofactor expansion. I have to keep breaking it down until it gets to something that's simpler I can write down. So I'm going to end up with -3 times this submatrix right there, -1 times the determinant of this submatrix, plus 5 times the determinant of this. And again, we're getting that by drawing lines through and seeing what's left over. There's a lot of videos on my channel that discuss how to do determinant computations, and we're just continuing to do that process here. 2x2 determinants, we know how to compute those. It's just the this term times this term minus this term times this term. So it's kind of this crosshatch little pattern. So we can go ahead and start writing out what this is. It's -3 times 4 times 0 is 0, -1 times 3 is 3. -1 times, again, 2 times 0 minus 1 times 1 is just a -1. And then plus 5 times, I'm going to have 2 times 3 is 6 minus 4. And if we simplify our computations, we get 9 plus 1 plus 10, which turns into 20. So we now know that this term right here, term 1, is equal to 20. Let's go ahead and do term 2. Term 2, this is the determinant I need to compute. I'm going to go ahead and do my cofactor expansion about the first row. I have 4 times this determinant plus 3 times. So normally on the second term we have to toggle plus and minus. Since it was already -3, it turns into a +3. And then finally plus 5 times this determinant. Again, we'll use what we know about 2x2 determinants and the fact that we can just write those down. We have 4 times 2 times 0 minus 1 is just 0 minus 1. And then plus 3 times, and negative 6 times 0, there's going to be zeros on both spots, plus 5 times a negative 6 minus 0. Do some simple addition and subtraction, and we end up with a negative 34 for this term. So now if we go back to our equation, we know that the determinant of A was equal to 1 times the first term, which was 20. We just computed that on the previous slide. And then minus 0, plus 2 times term 2, which was a negative 34. So I plugged that in right here. And then plus 0. So if we simplify, that is 20 minus 68, which is equal to a negative 48. So we've now computed the determinant of the 4x4 matrix A. And based on this number, we can now make a conclusion on whether the matrix A is invertible or not. The rule is if the determinant of a matrix is 0, the matrix is not invertible. If the determinant is non-zero, something other than 0, then the matrix is invertible. So since our determinant is a negative 48 is not equal to 0, so that means that the matrix A is an invertible matrix. And that concludes this short example.